Okay, so this problem reads, a freight train consists of two engines with mass 8 times 10 to the fourth kilograms. Each engine has that mass. And 45 cars with an average mass of 5.5 times 10 to the fourth kilograms. The first question is, what force must each engine exert backwards on the track to accelerate the train at a rate of 5 times 10 to the minus 2 meters per second squared, if the force of friction is 7.5 times 10 to the 5 newtons. So we're interested in the force that the engines have to exert on the track. So we want to recognize that the force that the engines exert on the track is equal to the force that the track exerts on the engines. Now, why is that going to be important? Well, the motion information that we have is about the train and the force, therefore, that the train feels. And so we need to recognize that the force the engines exert on the track is related to the force that the train feels. And it's equal in magnitude and opposite in direction. So this is the magnitude relationship. That's Newton's third law. So we can solve this problem by examining the net force acting on the train. And once we know that, we can determine the force as the track exerts on the engine, and therefore the problem, which is the forces the engines exert on the track. So let's approach that question with a force analysis. Now we want to remember that the problem also tells us that the force of friction, I'm just going to make sure I write that down, the force of friction that the train feels is 7.5 times 10 to the fifth newtons. And we're getting an acceleration of this train of 5.5, nope, that's not right, of 5 times 10 to the minus 2 meters per second squared. So I want to make sure all of those are accurate. All right, so to do a force analysis, we need to identify our object. So our object in part A here is the whole train, the entire thing, both engines and all 45 cars. So what forces are acting on this object, the train? So we know we have the force of gravity because the train has a mass. So the train and the earth are interacting for that force of gravity. We also know that the force the train has experienced friction. We're given that. That's between the train and the tracks. Well, we know that the train is sitting on the track, so there must be a normal force being exerted between the train and the tracks because they're sitting on the tracks. And then, of course, what led us down this path to begin with, we have the force of the tracks on the engine. So we'll call that the force of the tracks between the train and the tracks. Now, there are three forces that all are interactions of the tracks. That's going to be really important for us to distinguish. The frictional force by the tracks is along the direction of motion. The normal force on the tracks is perpendicular to that frictional force. If we're thinking of this train as if it's on a flat surface, it's perpendicular to that contact. And this force of the tracks is that Newton's third law pair of that is along the direction of the motion as well. So we're not looking at the net force of the tracks. We're actually looking at the different pieces that are contributing to the net force on the train. All right, so let's draw a free body diagram of our train. And again, this part one is looking at this force of the engines on the tracks. We're looking at everything together. So we have, if this is my free body diagram, I have the force of gravity. We know that the force of gravity is in the downward direction, and remember that's mg. We have the force of friction. Now, if the train, let's say, is moving to the right, The force of friction is opposite the motion. So we're going to say the force of friction is to the left. The normal force, that's the force just because the train is sitting there on the tracks. And then we have the force of the tracks on the engine. Well, if it's moving, accelerating in the rightward direction, that force is causing some of that acceleration. It's being hindered, of course, by the frictional force. So this is going to be the force by the tracks. They're in the rightward direction. I've drawn it bigger than the force of friction. Why? Well, we know that that train is accelerating along the tracks. So if I say my acceleration is to the right, my motion is to the right in this case, that acceleration means that the net force is to the right. Okay, so those are our forces. Now let's do our force analysis. So we're going to number our forces. All right, so we have force. We can look at both the horizontal and the vertical components of each of these forces, and there are 4 of them. So force number 1, there is no horizontal component. It's just minus mg. Force number 2 is in the positive direction. We don't know that magnitude, but there's no vertical component. Force number 3, there is no horizontal component, but it is in the positive direction vertically. And force number 4 is in the opposite direction of the motion, so we've drawn that negative, and there is no vertical component. Okay, so we can use Newton's second law now. The sum of the forces horizontal is equal to the mass times the horizontal acceleration, and the sum of the forces vertical is equal to the mass times the vertical acceleration. Now we're interested right now in the horizontal motion. We have that horizontal acceleration. The vertical motion is non-existent, so it's not changing its motion because it's not moving vertically, but it's not really going to be important for our problem. We are interested in this force the track exerts on the engine, so we can determine the forces the engine exerts on the track. So we're going to try to solve for this force of the track on the engine minus the frictional force is going to equal the mass of our train times the acceleration. Well, if I solve for the force by that track, I get the mass of the train times the acceleration plus the frictional force. So I need to determine the mass of the train. Well, this is the whole train. So I have 2 engines and 45 cars. So I need to take my engines times 2. I need to take the number of cars I have by 45. I get a mass of the train. So the mass of the train, I don't want to get off the board, so I'm just going to check my location, is 2.64 times 10 to the 6th kilograms. So how did I get that? I doubled the engine, so 2 times 8 times 10 to the 4th, and I added 45 cars. This whole thing is moving in one mass. So I get the force of the track on the engines is equaling 2.64 times 10 to the 6th times the acceleration of 5.0 times 10 to the minus 2 plus my frictional force of 7.5 times 10 to the 5th, and I get this total force on the train as 8.82 times 10 to the 5th newtons. That's the net force of the track on the engine. But there's 2 engines. So both are contributing to the force that that engine exerts on the track. And so if I divide for both engines, the force, oops, I'm getting a little too low. So this implies that the force by each engine is equal to 4.4 times 10 to the 5th newtons. So they each contribute to half of the force that the engine is exerting on the track, that total engine idea. Okay, that's part A. Part B says, what is the force of the coupling in between the 37th and the 38th cars? So imagine we're going all the way down those cars. They're connected by couplings. We want to know what is the force of the coupling between the 37th and the 38th car. We're going to make a couple of assumptions. We're going to assume that all the cars have the same mass, which we sort of did already once, and that the friction is evenly distributed among all of the cars and the engine. So if this is the total friction on the total train, if that friction is evenly distributed between the cars and the engine, then it's shared between all 47 pieces. Okay, so those are the two assumptions that we're going to make. So I'm going to quickly erase this so I have a little bit more room on the side. And we're going to write down our assumptions so we understand how they impact our analysis now of the coupling between that 37th and 38th car. All right. So let's write down our assumptions. We said that all of the cars have the same mass, and that mass is 5.5 times 10 to the fourth. So the first thing, let's draw our picture. So let's say this is car 37, and this is car 38, and there's all those cars behind it. We're interested in this force of this coupling. So that means that this coupling is interacting with all these cars behind. Okay, all of those cars are going to contribute to the force that that coupling has to push. Okay, it's going to push those cars. So how many cars is that? Well, we know that there are 45 cars. If we get rid of the 37 in front of it, we have 45 minus 37 of those cars. We are dealing with 8 cars that coupling is pushing, okay, as the train moves. So, or pulling, whatever, the force it's exerting on 8 cars. So the mass of the train section that we're dealing with is going to be that 8 cars times our 5.5 times 10 to the fourth kilograms. So the total mass that we're going to deal with is 4.4 times 10 to the fifth kilograms. So that's going to be the mass of the system that we're going to analyze. Okay, step 1, that's the first assumption. We said the second assumption is that friction is evenly distributed among all the cars and the engines. Well, there are 45 cars and 2 engines, so that friction is distributed among 47 items. So the friction on the train portion that we're interested in, so this is our new train, is going to be 8 cars times the contribution of the friction, which is 7.5 times 10 to the fifth. So this gives us the friction on one car, and I have 8 of them. So this gives us 47 divided by the total friction on the train, and I have 8 cars that are experiencing that. So the frictional force in our second part of this problem is 1.28 times 10 to the fifth newtons. All right. So now it's a very similar problem than we've already done. We're going to look at the force on this part of the train by that coupling. So our object is train 2, our second half of the train. So what forces does train 2 experience? Well, they're going to be the similar forces to what we had for the whole train. We know that we're going to have the force of gravity, between train sub 2 and the earth. We know that there is a frictional force between train sub 2 and the track. We know that there's a normal force, that train sub 2 is sitting on that track. And so that we're going to call the normal force. And now here's where it's slightly different than our first problem. We have the force of the coupling is what's interacting with that second half. So that is between the train 2 and the coupling. That's the force we're interested in this problem. So if we draw our free body diagram of this situation, it's going to look very similar to our other situation. We, of course, have the force of gravity, and we have the normal force. And those are going to look the same in magnitude because the train is not accelerating in the upward or down direction. Our frictional force is opposite the motion, and that coupling is going to be in the direction of our acceleration in this case, because that's what the train is doing. All right, so same concept as we did before. We're going to break these up into their horizontal and vertical components and analyze them looking for that coupling force. So we have our horizontal and our vertical components. Force 1, 2, 3, and 4 of them. Force 1, nothing horizontally. That's our force of gravity. Force 2, that's the one we're interested in. It's pointing to the right as I've drawn it. No vertical motion component. Force 3 is our normal force. It doesn't have a horizontal component. And force 4 is in the opposite direction of the motion as I've drawn it and is our frictional force. The sum of these forces horizontally is equal to the mass times the horizontal acceleration. Since I'm interested in that coupling force, we're going to ignore the vertical direction. It's not important for our problem. And so we have the force coupling minus the frictional force has to equal the mass, and this is of train 2, times the acceleration. And so if I solve for my coupling force, we have my coupling force is equal to the mass of T2 times the acceleration plus the frictional force. And we determined our total mass of train 2 was 4.4 times 10 to the 5th. The acceleration is the same, 5 times 10 to the minus 2. And our frictional force we determined for this portion of the train is 1.28 times 10 to the 5th. And so we find that our coupling force then is 1.5 times 10 to the 5th newtons. All right, so the process, once we kind of deduced and picked apart what our object of interest is and what's experiencing that net force, the process is the same, identifying those interactions and going through that that force analysis where we separate the forces, use Newton's second law to solve what we're interested in. So key features to be thinking about. We were first asked about the engine on the track, which is the same as the track on the engine, so we can look at the forces that are causing that change in motion of the train. We want to recognize we're dealing with a whole massive train, and that first part's all 44 cars and 2 engines. And then for part B, really looking at the unit of what's behind that coupling for cars 38 to 45 and evenly distributing that friction among them. All right, good job.